Well, guys, it is the end of the first quarter, and it is time for us to, buckle down and finish Unit 2. So we're going to talk about recognizing similar figures today. Okay, this is actually this week is the last week of the first quarter, but this video is for quarter 2, week 1. Okay, so it's not time to buckle down. It's time to gear up. You got a fresh start, right? Let's go. All right. Sorry about that. So we're talking about recognizing congruent or similar figures, which is section 2.3. And so I need you to write down two definitions. Okay, first of all, figures are similar if one, their corresponding angles are congruent and their corresponding sides are proportional. Note, proportional means ratios are equal. I should say the word are there. Ratios are equal between, oh yeah, that's what proportional means. Further note, ratios are fractions of corresponding items, right? Further note, proportion implies you have a fraction equal to a fraction. Okay, so there's some important words that you'll see. So this is just for example, let's say I had a rectangle that was 3 by 2 and another rectangle that was 6 by 4, and I wanted to set up a proportion. I could say that 6 over 3 is equal to 4 over 2. This is an example of a proportion. Ta-da. Okay, and you sometimes we're missing a number and you have to cross multiply, but that's not but a proportion is just two ratios. So the ratios of these two sides, and then they're equal to each other, right? And we know that 6 divided by 3 is what? It's 2, right? And 4 divided by 2 is 2, and 2 equals 2, which means, so they're equal, right? So that's proportional anytime two things are equal. But in this chapter, we are going to go into this definition of similar. Figures are similar if one can be obtained from another through a series of transformations that includes a dilation, including a dilation. Okay, so in this video, we are going to look at 4 pages, but there's a lot to write down, so we're just going to do some takeaways. We're going to look through them and write down some takeaways, and then we are going to do questions 1, 2, and 3 on page 71. And actually, I should say, let's do a similar triangle exercise. All right, so these are the things we are going to do right now. So I have a triangle here that I've already measured where the sides are 3 centimeters and 4 centimeters. So I took my ruler and I measured, and you can see that side is approximately 3 centimeters and this side is 4 centimeters, right? So now I'm going to cut it out, and it's going to be my first triangle. Okay, there. And we know that this side would be 5 centimeters because 9 plus 16 equals 25, right? Pythagorean theorem. So now I'm going to make what I know will be a proportional triangle by multiplying all of these sides by 2. So I want to make a triangle now that's 6 and 8, and then I'm gonna make sure that my hypotenuse will then be 10, right? So I'm gonna go make this try. This segment is gonna be 6 inches long. So I'm gonna make a little mark there because that's gonna make that side 6. And then along the bottom, I'm gonna make my base 8, starting at 0, going all the way over to the 8 on the ruler and making a mark. And now I'm gonna take my ruler and from one mark to the other, I once had a friend named Mark, I am going to draw a segment. Okay, so this is 6 centimeters. This is 8 centimeters. And so I do know that that would make this 10 centimeters. Again, because 36 plus 64 equals 100, right? A squared plus B squared equals C squared. Now, I'm going to cut my triangle out. Hands-on learning. Can't beat it, right? Okay. So, these are similar triangles, but what the book is saying is that, maybe I have the triangles like this, right? And then we're asked, are these two triangles similar? Well, the answer is yes, if we can identify a series of transformations in which we can get from one to the other. Okay, that will have to be. So there's my 3, 4, 5. And now I'm going to take and actually let's do a transformation. So here's my 3, 4, 5, right? Now I'm going to, what's this called? Translate, right? And then I'm going to rotate it. And then I'm going to dilate it by 2. So you saw me, I shifted it over, I turned it, and then I replaced it with this triangle, which is double the size, which in essence is dilating it. And so we had a translation. Let's just write translation. Then we had a rotation. And then number 3, we had a dilation. So if this is triangle A, and this is triangle B, right? So this is triangle A, this is triangle B. The question is triangle A similar to triangle B? Is it? The answer, well, we know these two triangles are similar, right? This one is just twice as big. But using our definition, two triangles are similar if they're connected by a series of transformations. Well, we kind of went the opposite direction. We know these are connected by a series of transformations because I literally translated A, then I rotated it, and then I dilated it. So we can say, yes, they are similar. This is a 3, 4, 5, and this is a 6, 8, 10. So we can say, yes, triangle A can be translated, rotated by 90 degrees, right? Yeah, clockwise, I think, right? And dilated to form triangle B, okay? So I literally translated triangle A, rotated it, and then multiplied it by 2 and ended up with triangle B. So these two triangles are similar. They're the same shape, but different sizes. So now let's look at our beloved textbook pages here. So we start out with this, anyway, with Spark Your Learning, talking about designing a phone case. So we could take a pattern of parallelograms and we could translate them, but we could also make similar ones, by expanding or contracting our original shape. And then we can make a pattern and design a phone case. But we're not going to actually do that. What we do need to look at is, given several shapes, how can we tell if they are similar? Woo, just making sure I'm reporting. Okay, so again, we're not going to copy down all these shapes right now. But just looking at all of them, can you tell which ones are similar? Well, right away, I can see that A and F are congruent. I'm just going to write that down. Triangle A is congruent to triangle F. They're the same shape, exactly, just translated, right? Triangle E, that also looks like the same shape, but bigger. So triangle A is similar to triangle E. These are the same shape, different sizes. So I could say, I could translate triangle A over here and then dilate it, and I would end up with triangle E. Just the same way I just did, right? Triangle C also looks to be similar, but that one's just reflected, right? So it's just flipped. Triangle D and B, they don't look like they're the same shape. So they are not in the family, okay? So let's just write that down on page 66, the takeaway here. Page 66. Triangle A is similar to triangle E by a translation and dilation sequence. In other words, you can translate triangle A and then dilate it to get triangle E. Triangle A is congruent to triangle, which one was it? Triangle F, right? Triangle A is congruent to triangle F by a translation. So if you don't need a dilation, if you can get from one shape to the other using only translations, rotations, and reflections, then they're going to be congruent. If you need to use a dilation, then the figures will be similar. Okay? All right. So one other takeaway would be this car show. Or one other thing to note and get a takeaway from is this car show problem. So again, we have 1, 2, 3, 4, 5 rectangles in the question. They're different sizes and shapes, and circle all the posters that appear to be similar, or the posters you identify. Describe a sequence of transformations that takes one poster to the other. So as I just look at these without measuring, just inspecting, I can see that the blue one right here and the purple one right here are the same shape, but different sizes. So I could translate and reduce the size of this blue poster, and I could obtain or make it exactly the same as this purple poster. So I would say that the blue and the purple are the same. All right, so we already kind of wrote that down. So we're not going to write that down again, but what we're going to do now is end with problems 1, 2, and 3 from page 71. Okay, so let's read this and then we'll add it to our notes. Use a coordinate plane to design the background image for a video game. How fun. Start with triangle ABC. Okay, so I'm going to pause the video and I'm going to add triangle ABC into my notes. All right, so now we have in the notes, number one, I have drawn the triangle by making an XY axis that goes up to 5 and labeling point 0, 1 as C, 2, 1 as B, and 2, 2 as A. And then I also wrote the coordinates down here because we're going to do some transformations of it. Okay, to draw triangle DEF, translate triangle ABC using the mapping notation XY goes to X minus 2, Y. Then apply a dilation with a scale factor of 2 and a center of dilation of 0, 0. Draw and label triangle DEF. Okay, how fun. All right, let's do it. So triangle DEF. Okay, first of all, we have to translate. So X minus 2, Y. This is step 1. Okay, so I'm going to call the first, after I do this one, I'm going to call it A prime, B prime, C prime, because we still are going to have to dilate it after we do this. So this is not going to be the end of the line here. So the first thing we have to do is subtract each X coordinate by 2, which is going to shift left 2, right? That's what they want us to do. No worries. So 2 minus 2 is 0. 2 minus 2 is 0. And 0 minus 2 is negative 2. Whoop. Negative 2, 1. Okay. Let me let me rewrite that. C prime is negative 2, 1. There we go. Sorry about that. Okay. So then step 2, what do we have to do? Scale factor of 2. So now we're going to take and we need to dilate by 2. So I'm going to multiply everything by 2. And then that's going to make triangle DEF. So A prime is going to become, we're going to call point D by just multiplying by 2. So 0 times 2 is 0. And 2 times 2 is 4. And then now I definitely messed something up here, right? 2, oh, this is a 1. Okay. 2, so that's going to be 0 again. 0 times 2 is 0, and 1 times 2 is 2. Aha. All right. And then C prime, 2 times negative 2 is negative 4, and 2 times 1 is 2. Okay, so yeah. So that's how we get triangle DEF. Little sloppy, but you know, it is what it is. We thought about it together, okay? So triangle DEF, we're going to plot this now, and it should look like it's shifted 2 to the left and is going to be double the size. So let's plot it. 0, 4, 1, 2, 3, 4. Okay, so there is 0, 4, and that's point D. E is at 0, 2. 1, 2, so okay. So there is E. And F is at negative 4, 2. So let's go 1, 2, 3, 4, 1, 2. And got a little scared there for a second, thinking I messed something up. But you can see that triangle DEF is indeed twice as big as triangle ABC, and it's shifted 2 units over. Yay, we did it. Okay, and we know they're similar, right? Because they're connected by a translation and a dilation. All right, let's do step B. To draw triangle GHJ, reflect triangle ABC using the rule XY goes to X negative Y. Then apply a dilation with scale factor of 2. All right, here we go. So we're gonna reflect and then do a dilation, and this is GHJ. Okay, triangle GHJ. So we need to do a reflection. XY is going to, what is it going to? Going to X negative Y. X negative Y. Okay, so starting here, but now I'm going to do my same thing. A prime, B prime, C prime here. Okay, so all the Y coordinates are becoming negative. So 2, -2 becomes, 2, 2 becomes 2, -2. B becomes 2, -1. And C becomes 0, -1. Now I have to, so that's the first part. Now I'm going to multiply by 2, right? So that will give us GHJ. So there's going to be 4, -4 after we multiply both of these by 2. This would be 2 times 2 is 4, -1 times 2 is -2. 0 times 2 is 0, and -1 times 2 is -2. So now when I graph this triangle, triangle GHJ, it should be flipped and double again. So 4, -4. Let's go over 4. 1, 2, 3, 4. And down 4. 1, 2, 3, 4. Oh no. I'm going into my notes. This is terrible. 4, -2. All right. 1, 2, 3, 4. 1, 2. Okay, that's not as bad. And then J is at 0, -2. 1, 2. Well, sometimes when you transform a shape, you just end up right in the middle of your notes or at the top. Okay, but in any case, we can still see that this new triangle, triangle G, which is right here, H, J, is flipped and dilated, and so we can see that these are similar. So the question is, if these are similar and these are similar, are these two triangles similar? And the answer is yeah. If one thing is similar to 2 other things, all 3 of them are similar. So this is or A, B, and C. We can say all 3 triangles are similar. And how would we say that? Well, we already know that the 2 pairs are similar because they're connected by, 2 transformations. This one, a translation and a dilation. The second one, a reflection and a dilation. How are these 2 triangles connected? Well, we know they're the same size because they're both double the first one. Actually, they're congruent, right? But the thing is, congruent figures do fit the similarity definition, although they don't need a dilation, so they're really congruent, with a scale factor of 1. In any case, the connection between this triangle and this triangle is a translation and a reflection, right? So let's just say that triangle DEF can be obtained from triangle GHJ by a translation and a reflection. All right, so actually, if we are going to say that figures are similar, if one can be obtained from another through a series of transformations, including a dilation, then no. I guess those two figures would not be similar because we did not need a dilation to get from one to the other. But going by the other definition, we could say they are similar. They're just also congruent because the scale factor is 1. In any case, if you can list out your series of transformations, you will get full credit. All right. I think that is good. So we've talked about the series of transformations. We have done a series of transformations, including hopefully you also cut out these triangles and actually did a series of transformations. And so let's just go ahead. If you don't mind skipping 2 and 3, I think we're ready for a series of transformations and similar figures summary and success criteria. All right, let me pause so you don't have to watch me write it out, and I'll be right back. All right, this is where we're gonna land here. So, series of transformations, summary, and success criteria. First, I can identify transformations, translations, reflections, rotations, and dilations. I can perform transformations on points and shapes. And we have done each one of those separately, right? So now it's just about writing that we can do that. And if not, ask about the one you can't do. I can perform a series of transformations by doing 2 or more transformations to a shape. I can identify if 2 figures are similar by describing the series of transformations that connects them, including a dilation. That's what the book says. And we're just going to put a little star. If the series does not include a dilation, the 2 figures are not just similar, they are congruent. And that's it. That's all we're going to do in class. We will also be looking at the Module 2 review, and then we're done. We're moving on to linear equations, applications, and functions, and a whole new set of mathematical fun. So I hope you've enjoyed our geometry unit, our first geometry unit, and I'll see you in class.